Yep. Good evening, everyone. Sushani Camps, let's start off. So last class we have finished with elasticity. We'll be starting off with capacitors today. I hope everyone saw the message right in the group. The event is shifted to July 9th. We are keeping it in the evening, 5 to 9 p.m. So try to reach by 5 sharp. So once you come, we have sandwiches and drinks, cool drinks. And then 6 o'clock, I think your seniors will be there by 5 o'clock. So you can talk to them, interact with them till 7 o'clock. And then 7 o'clock, we'll have a proper dinner. So everyone make sure not to have your lunch. Don't eat and come. If you come there and if you don't eat enough food, I'm going to punch you. Keep that in mind. It'll be pretty good. Last time when I kept it on Sunday, they had almost like, because last Sunday we had a farewell for your medical batch. So I think sweets they had around 11 varieties of Indian sweets. And then that cakes, desserts and everything. So total milake, only dessert ka stuff is cross 20. So they had enough. So if possible, try to have a light breakfast. You're hungry, you come early by 5 o'clock, there are sandwiches. And 7 o'clock, make sure to eat a lot. So there, so everyone try to make sure to attend. I think almost 9 to 10 of your seniors are coming. Few of them are from IIT Bombay, IIT Delhi and IIT Madras. So you can meet them, you can talk to them. Any queries, anything, general interaction, you can interact. And also, I think we have never seen each other physically also. It's been always online, so we can see. Let's start it off. I hope everyone is there. Do keep your cams on. Again, I'm telling you, you have to continue solving parallelly with me. Whatever chapters are going on, chapters will be going pretty fast. So let's see what is this capacitor. Capacitors, the chapter itself is kind of, it's okay, easy, but it is important because the same kind of circuits, exactly everything will repeat again in current electricity. So the circuits will look quite similar there, the logics and all. So what is a capacitor? Ever seen a capacitor in real life? You've seen it. Fan ke upar hote hai na capacitor. If you ever seen the fan on the top of a fan, there's a white cylinder. Sometimes what happens, right? Your fan rotates pretty slowly. Then they say, we have to change the capacitor. If you go to a shop and ask him, he'll give you a cylinder thing. So on top of a fan, if you see, there's a cylinder. So a capacitor is simply, it is a device which stores energy in the form of electric field. So what do you mean by energy stored in the form of electric field? So one thing, if you observe, let's say if you have a conductor, let's say we connect a bulb here with a switch, and if this is grounded, and let's say this conductor is having some charge, plus Q. So you'll observe for the conductor, there are field lines like this. Now, the moment you close the switch, what do we observe? The moment you close the switch, the charge starts flowing through the bulb. There will be a current flowing through the bulb and the bulb starts glowing. And at the same time, if you observe, the charge on the thing also starts decreasing. And eventually, finally, right, the whole charge goes into the ground here. bulb does not glow anymore. And at the same time, you'll observe the charge becomes 0 and the field becomes 0. Are you getting the scenario here? So if you take a conductor, give it some charge, and if you put a bulb on the other side and close it, grounded, we'll observe the charge will flow from the conductor into the ground. And eventually all the charge becomes 0. So if you observe something here, we observe when the switch is closed, the bulb glows. If the bulb is glowing means you're getting energy from somewhere. And at the same time, remember July 9th, not this Sunday. Don't come this Sunday and be there and roam around. Then you call me, sir, no one is here. What should I do? Next Sunday, be careful. At the same time, the field lines start decreasing. And when the field becomes 0, the bulb stops glowing. So from this, we can conclude, we can infer somehow the field is stored in the energy is stored in the form of field. So when we said, till now electric field, we can also think like this. Electric field is nothing but another form of energy. Energy is stored in the form of field. So that is the meaning of this first statement here. See, it is a device which stores energy in the form of electric field. For example, if you take a dam, water dam, it stores energy in the form of what? Gravitational potential energy, right? If you take a water dam, it has full water here. So when you release the water, you get energy. So where is that energy stored? In the form of gravitational potential energy, mgh. If you have a rotating wheel, the energy is stored in the wheel in the what form? Kinetic energy, half mv square. So every device stores energy in some form. So a capacitor is a device which stores energy in the form of electric field. So I'm just trying to show you an experiment, like, where actually how that energy is related to field. I hope that the introduction is clear. So somehow the field is nothing but a form of energy. Now, how it is exactly related, we'll be seeing that later on. Clear?
It means energy flows from that conductor to bulb.
Yeah. Then, so if you have a body here, and let's say if you give charge Q to the system, consider a charge Q. Given to a system, we can say the potential V is proportional to the charge. So if I give more charge to a conductor, won't I get more potential? KQ by R types. This is the potential of the conductor. So the proportionality constant Q is equal to CV. So C is equal to Q by V. This is your first formula. C is called capacitance. Which depends on dimensions of the system and the nature of the material. So what is the meaning of C? Think of like this simply. Higher the C, the more, see the capacitance, capacity. So higher the capacitance, the more, it can store energy per unit potential difference. So whenever you think of what do you mean by capacitance, simply think of like this. The capacitance tells you what is the capacity to store more energy. Higher the capacitance, more energy you can store per unit potential difference. more energy can be stored per unit potential difference? There, this is your first formula. Q is equal to CV. Q is the charge on the conductor and V is the potential of the conductor. And C is some proportionality constant. Clear with this? Now, ever seen a capacitor, how it looks? If you ever broken a keyboard or some kind of computer device or anything, you will see this thing. Seen these kind of things?
Oh,
The
yes,
blue
sir.
color cylinders, these are one of the most common things you must have seen. You can break your TV remote and check it out today. So you will find, this kind of circuits and all. Clear? Now, the symbol for capacitance is two parallel plates, like these two parallel lines. The units are farads. Generally, a farad is a pretty large unit. Generally, capacitance value is in the range of microfarads. That is 10 power minus 6 farad. Clear? Now, before going ahead, there is one important element which we'll keep using everywhere, an ideal battery. What's an ideal battery? So it's a device which maintains a constant potential difference across the terminals. Listen to this word, it's very important, because battery is something which we'll see in literally every chapter in electromagnetism. So people have certain misconceptions about a battery. So this is the symbol for a battery, one small line, one big line. The big line is the positive terminal, the small line is the negative terminal. So what is the meaning of this exactly? If you say the battery ka voltage is V, the meaning of this is, if the negative terminal is X, the positive terminal is V plus X. Are you getting it? So it maintains a potential difference of V. What most people think, they think negative terminal is 0. So V plus minus V minus should be equal to V. Example, if you have a battery like this and if I ground this, let's say this is 3 volt. What is this potential here? If you ground something, what is the potential? 0. If that is 0, how much is this then? Anyone? Everyone should try. What is this? If the positive terminal is 0, what about the negative terminal?
-3.
-3, na? Are you getting it? Negative terminal of a battery 0 nahi hai. The most misconception people have is negative terminal is 0. Not necessary. What about this guy? Let's say we have a battery. We have a battery. We have a battery. 3 batteries like this. This is grounded. This is 2 volt. This is 3 volt. And this is 5 volt. What is the potential here? Everyone, what is the potential here?
0.
0, because it is grounded. So what is the potential here?
-2.
Minus
-2, na? What is the potential here?
-3.
-3.
What is the potential here?
-5.
-8.
Please check this example. Yeah. Please have a look at this example. So a battery maintains a potential difference. Battery does not make zero potential. Battery doesn't care. You can ground something and make it zero. A battery simply maintains a constant potential difference. Have a look at this statement here. All clear with this? So this is the main concept of a battery. So whenever you put a battery, you can simply understand it will increase the potential by V. Now, capacitors are of, we will be studying, there are three types of capacitors we study. Parallel plate capacitor, spherical capacitor, and cylindrical capacitor. So the first thing we will study is a parallel plate capacitor. Again, entire electromagnetism, right? It is mostly about the standard formulas and the standard models. If you can remember the standard results and the standard questions, you'll be able to handle the entire electromagnetism. Unlike mechanics, right? There is there's a less scope of twisting the problems. You can, but there's a less scope. So what is a parallel plate capacitor? Consider two parallel plates with a distance d between them. This d is very small compared to the dimensions of the plate. Now, what do you mean by that? If you take two parallel plates, if you give the charges plus and minus here, how will the charges be? So this will be plus, this will be minus. The problem here is the field here will be uniform. The field on the edges now will become like this actually. The field on the edges will get messed up. This is called fringe effect. So if d is large, the field won't be uniform. If the distance between the plates is large, the fringe effect will be pretty large here. E is not uniform. So in order to study uniform fields, for small d, we can neglect the fringe effect. So this is the first condition. Okay, so whenever you are studying parallel plates, you make sure the distance is very small. We neglect the fringe effect and assume the plates are infinite sheets. Please check this thing. What is a fringe effect? Divanshu, Abhiksha, I can't see you guys, right? Your cams are blank. Chirayu, your cam is off. Ammu, Gauri, once finish your dinner and switch on your cams. Any doubts on this fringe effect, please ask. Clear? So, can I turn the page?
Sure, 1 minute. Yes, sir.
Now listen carefully. How does this capacitor work and how does it store energy? Consider a battery V connected to the two parallel plates. Now see what happens here. So the moment you connect a battery here, this is the positive terminal, this is the negative terminal. The electrons which are sitting in this plate, what will happen? They get attracted by this positive terminal. So electrons will rush through the battery and will get accumulated here. Now try to understand one thing. A battery is like a water ka pump. A battery does not produce, charge. Are you getting it? Battery does not produce charge. Tell me one thing. If you have a water pump between two water tanks, and if you keep a pump here, what does the pump do? It simply pushes the water from one place to another place, right? Does it produce its own water? It does not produce water. The same way, whenever you put a battery across a wire, it simply pushes the electrons from one side to another side. Are you getting it? Battery does not produce charge. Battery simply, pushes the charge from one side to another side. Now see what happens here. I'll give a crude example. So think of like this. Imagine we have two rooms here. And in this room, there are 100 people. And in this room, there are 100 people. So I'm here in this intersection. Let's say I'm a very strong person. What I do, whoever comes near the door, I'll catch them and push them into this room. Initially, what will happen? Nothing will happen. They'll become 90, they'll become 110. So if I try to push one more person, what will happen? There'll be slight discomfort, right? Because there it is little getting crowded here, itna crowd nahi hai. But since I'm very strong, I'll push people. So this will become 70, this will become 130. Now, if I try to push more people, what will happen? At this point, these people in this room will start pushing you back, isn't it? They'll say, yeah, don't come here, it's already crowded. But since I'm very strong, I'll still push them more. Then this will become 50, this will become 150. Now, if I try to push more people, what will happen? Won't this resistance increase? But since I'm still strong, I'll somehow push people there 30 and 170. Now, at this point, the opposition will be so strong. With whatever force I'm pushing, they will also push back with the same force. At this point, what will happen? No more electrons will go, no? We reached a steady state. Are you getting this? You're getting what is this? So in this scenario, I am the battery, the people are the electrons. And the two rooms are the two plates. So what happens here, since the electrons start going here, this is what will happen. This will start getting some charge to small q and minus q. But since the battery is still strong, electrons are still moving here. And these things generate a counter field inside. Is that making sense? But since the battery is still strong, this is an intermediate stage. At one point, there will be so much charge transferred plus q and minus q. At this instant, you reach a steady state. The force due to the battery and the induced charges on the plates will cancel out each other. So we reach a steady state. What is the meaning of steady state? If you remember, you have discussed this in fluid mechanics. What is a steady state?
Inflow equal to outflow.
Matlab, the properties will remain constant, right? Nothing will change anymore. The situation has reached a constant state. Are you getting the scenario here? So initially, the electrons are attracted by the positive terminal of the battery and electrons go from left to right side. In steady state, the induced charges, right? There will be so much, and the charges, the induced charges oppose the electron flow. Please have a look at this page. So whenever you connect a battery between the two plates, this is what happens there. Any doubts on this story here? Please ask me. So initially you took two neutral conducting plates. The moment you connected a battery, electrons will start going from left to right. As the electrons are going, the charges accumulated will try to oppose, but the battery is stronger than the induced charge. At one point, so much charge will accumulate, the induced charges and the battery will cancel out each other, reaching a steady state. Sure with this? Any doubts on this page? Please ask. Again, if you see the whole story from the beginning, we defined something called a capacitor. So we defined capacitor is nothing but a device which will store energy in the form of electric field. And how do you know it is stored in the form of electric field? Frankly speaking, we can't prove it directly. So we took an experiment. We said we took a conductor, we connected a bulb to it, and then we closed the switch, the bulb started glowing. So think about it. Why will the bulb glow? If the bulb is glowing, meaning there's energy coming from somewhere, isn't it? So when the bulb is glowing, we observe the field lines are decreasing in the region. So we can infer from this experiment. See, think of it. Let's say in your house, your mom kept, 4 dairy milk chocolates in the fridge. Right? You and your sister are there in the house. Next day, 2 chocolates vanished. What can we infer from this? The fridge ate the chocolates. The chocolates suddenly vaporized and went into somewhere. Third, the 2 kids in the house have stolen the chocolates and eaten it. So we can infer something. There is no need to prove like, the Arish is showing the chocolates. So there is Kit Kat types. So getting it, we can infer from the data there. There is nothing like, happens a lot, right? So chemistry mein, you saw the J.J. Thomson model, Rutherford model. Rutherford model says electrons are going around the nucleus like a planet's going in an orbit. Did Rutherford really went inside and saw the planets or what? No, right? But what he did when he did this experiment of, this alpha particle bombarding experiment, the scattering experiment, he found out that most of the alpha particles are just going through. So from there, he makes a conclusion. That means there should be a lot of empty spaces. And some of the alpha particles are having huge deflections. From there, he concluded that means all the nucleus is at the same point. That's you're getting big repulsions. So you can conclude things, even though you can't see. So same way here, we can conclude the bulb is glowing as long as there's a field lines. When field lines become 0, the bulb stopped glowing. Or somehow energy is there in the field. Now, how and what, that's a different story. We don't know that. Right? And then we defined a capacitance, right? If you have more charge, you have more potential difference. The proportionality constant is C. C is called capacitance. The symbol, then we defined about a battery. And then we said there are 3 types of capacitors and parallel plates. And this is the story that we wrote. Clear? Any doubts on till now? We didn't start anything, maybe just introduction about what's a capacitor.
So it means after some time electrons will not flow.
They'll not flow, no? They're in a kind of a steady state, right? Battery and both are pushing each other. Fringe effect is nothing but if you keep the plates very far, what will happen? The field in middle won't be parallel, no? Field will actually start going in the corners like this. That is called a fringe effect. So if there's a fringe effect, we can't study. Because we can't find the field, it will be non-uniform. So we keep the distance between the plates very small so that we can neglect the fringe effect and assume the field is uniform. Okay. Now, so finally you reach a steady state. So this is the battery B. Let's say this thing has charge plus Q, this thing has charge minus Q. On two parallel plates, if the charge is plus Q minus Q, what will be the charge distribution? You guys remember we did this in Gauss law?
Total
What
by
is the charge
2.
outside? Outside is total by 2. So this should be Q and this should be minus Q. So all the charge will be here. So if you have a sheet here with charge plus sigma is Q by area, the field will be sigma by 2 epsilon. This is the field due to infinite sheet. If this is minus Q, we get a minus sigma. The negative plate will attract. This field will be sigma by 2 epsilon. So field between the plates is given by sigma by epsilon, where sigma is nothing but charge by area. So, and we know the field between the plates is nothing but potential difference by distance between the plates. E is dV by dr. So in case here, since E is uniform, you can directly write like this. So sigma by epsilon, potential difference between the plates is V, distance is D. Sigma is nothing but Q by area is V by D. So from here we get Q by V is equal to A epsilon by D, which is nothing but C. So there we proved the capacitance of a two parallel plates, the proportionality constant C is given by A epsilon by D. This is your second result after Q is equal to CV. So if you have two parallel plates with A is the area of the plates and D is the distance between the plates, the capacitance of such a system is given by A epsilon by D. So all the story is to find the capacitance of a system. So here we remember we said C is a proportionality constant. Now how to find that? The proportionality constant is given by A epsilon by D. Have a look at this. Clear? Any doubts on this? No. So if you give me two parallel plates, so indirectly what I'm saying is these two parallel plates have a capacity of A epsilon by D to store the charge. So C is equal to A epsilon by D. This epsilon ka value is given by is the permittivity of vacuum 8.85 into 10 power minus 12. Example, they can ask a question like this thing. Let's say C is 8.85 microfarad. Distance between the plates is 1 centimeter. They'll say find area. Now, if you substitute the formula here, A epsilon by D, 8.85 into 10 power minus 6. Area epsilon is 8.85 into 10 power minus 12 by 1 centimeter. is 10 power minus 2. This turns out to be 10 power 4 meter square. If you see, it is pretty large. 10 power 4 meter square matlab 100 meter square. So you have to take a 100 meter ka square plate. Just to get how much? Just to get 8.85 microfarad. So if you want to increase the capacitance, increasing area is a bad idea. So increasing area to increase C is a bad idea. It's not economical. So whenever you want to build a large capacitor, increasing area doesn't make sense. Clear? Any doubts on this page? Next one. This is important. Same question. If I say capacitance is 8.85 microfarad, let's say area is 1 meter square. I want to find D. Again, C is equal to A epsilon by D. 8.85 10 power minus 6. Area is 1. Epsilon is 8.85 10 power minus 12 by D. You get D is 10 power minus 6 meters. Now that is almost 1 micrometer. Now there is a problem with this. If you make the distance too small, you actually have another kind of issue. This also doesn't work. I'll show you why in the next page. Since we get a dielectric breakdown, we'll see what is a dielectric breakdown. So the only option left is to increase C, introduce a material between the plates. Then your capacitance becomes A epsilon medium by D. This is nothing but epsilon R into A epsilon by D. Hope you remember that. Epsilon medium is epsilon relative into epsilon naught. Epsilon R is called dielectric constant. So by putting a material between the plates, you can increase the capacitance. Example, if you take zinc sulfide ka epsilon it is approximately 4,000. So if you can fill up the space between them with the zinc sulfide, you can increase the capacitance by 4,000 times. So there are 3 ways you can increase the capacitance: change the area, right, or increase the distance, decrease the distance between them, or change the material between them. Check this out. Now, what is the problem if you decrease the distance? Any doubts on this page, please ask. Let's see. What is the problem there? Dielectric breakdown. What is this dielectric breakdown? When you apply high electric fields, the electrons are pulled apart from the nucleus, making the region conducting. What do you mean by that? Think about it. If you take an atom and an electron, the electron is going around the nucleus. This is a scenario when there is no electric field. If you don't apply any electric field, they'll be normal like this. But if you apply some electric field, this is what will happen. The nucleus and the electron, right, they will actually get distorted like this. So let's say if you apply an electric field like this, the force will be E. The force on the electron will be in the opposite direction because negative charge E. So you create a dipole. Is this making sense? So if you put a neutral atom in case of electric field, the atom will actually split little distance because of the electric fields, creating a dipole. What happens if you apply very high electric field? If you apply very high electric field, the force will be so high, the nucleus and the electron simply get separated. You getting this? This will make the whole region conducting. So the air, which is a bad conductor, suddenly becomes a conductor. And because of this, what will happen? The charge will start leaking. You get sparks. This is what happens during a thunderstorm. The potential difference between the earth and the sky becomes almost 9 million volts. 10 power 9 volts. The voltage is so high, the air literally, right, breaks down, the air becomes conducting, and you see that lightning storm, that lightning bolt or whatever. The sound which you hear, the dart, big sound, that is actually dielectric breakdown. So whenever there's a dielectric breakdown, you hear that big sound. So this whole thing becomes ions. Let me show you how that looks also. So here we define something called dielectric strength of air. So whenever you say dielectric strength, the meaning of this is the maximum electric field right, that can be applied before breakdown. If you apply anything more than this, the air becomes conducting. Example, if you take dielectric strength of air, it is 3 into 10 power 6 volt per meter. Means if you apply 3 into 10 power 6 volts across 1 meter, air becomes conducting. Got this? Now in our previous example here, if you take, I'll show the previous page. If you take a battery voltage is 10 volts and the distance d between them is 10 power minus 6 meters, the electric field is given by V by D, turns out to be 10 power 7 volt per meter, right? And the air ka dielectric strength is 3 into 10 power 6 volt per meter. So the air becomes conducting. So you can't decrease the distance between the capacitor plates. If you decrease too much, there will be dielectric breakdown and the charge will start leaking. Yeah, air means air only, na? Atmosphere ka air, oxygen, and all that stuff.
What's up everybody, welcome back to my laboratory where safety is number one priority, and today we're going to experiment with the Udin coil or Tesla coil and a graphite pencil. What will happen if we put 50,000 volt to the graphite
So that thing he's showing is called a Tesla coil. It generates around 50,000 volts.
pencil? Let's check this out. We got here graphite pencil and Udin coil. Let's see what happens. Okay, let's try this in the dark. Whoa. It's just high.
You can see that sparks. That is what happens. You can see that sound buzz. That's actually a dielectric breakdown. So when this happens at such a huge level, right, that's what we call as a thunderbolt.
In the pencil. Whoa. Ow. That's painful. 50,000
You should not be touching like that.
volts is painful.
Here it is sharp. Look at this thing. You can clearly see here.
Wow, isn't it beautiful? Look at this.
Can you see what is happening? What is happening here?
It is
Graphite.
conducting.
Graphite is a good conductor, right? So the spark is going from one end, going through the graphite and coming from the other end and hitting the ground because ground is zero potential.
Going to the pencil and coming out to the other side. Let's put another pencil over here and let's see what happens. Wow, look at that. This is so cool. It's just going to the pencils.
And when you're putting so much charge, what happens?
Yeah!
It starts burning.
Look at
These
this.
guys are having fun.
This pencil just lighting up. The whole pencil is on fire now. Yeah, this is cool.
There. So normally, right, whenever you have an electric shock or something, I tell this to the medical students normally. If a patient comes to you, right, with an electric shock or something, the first thing you generally should be treating is for burns. So most of the people, right, they have a 3rd-degree burns. So when you get a high electric shock from high voltage, more than the shock, right, what kills them is actually the burns. It produces so much temperature, flesh literally burns. So that is what we can see, that there's a huge resistance. So that phenomena which I showed you right now is called dielectric breakdown. That buzz sound and all that spark which you're seeing. That is what happens if you apply a high voltage across a small distance. Clear? Reena, want to say something? Reena, something?
So the sparks they are
Your voice is breaking a lot, Reena.
state the spark.
Just message me, na? Your voice is breaking a lot.
So can you hear
Yeah.
me?
हाँ बेटा बोलो ना बोलो बोलो Okay, let's see. So that is the first thing. Reena, you're saying something.
Four
So
I
I
had.
messaged.
Message to co-host, no? Always message to the co-host. So that is one thing. Next thing, force between the plates. So if you have two plates with a charge plus Q and minus Q, there'll also be attraction between them. Are the sparks in the plasma state? You can't exactly say plasma, but yeah, kind of right now. Basically, it literally becomes ions, right? But it is temporary. Once you remove the charge, it goes back to the normal state. Okay. Plasma is like little too extreme. There, literally all the electrons are ripped apart from there. Here, it is only just it becomes ions and conducting. So when you have a plus and negative here, how do you find the force between the plates? The force on any one plate, if you take the force on the right plate, that is field due to the left plate. Remember, you should not take the field due to yourself into charge on the right plate. So the field is given by sigma by 2 epsilon into minus q. Sigma is nothing but q by a minus q square by 2a epsilon. This is the force between the plates. Put it up. Let's see some questions before going ahead. There is still a lot more theory, but I think you'll get confused. Let's do some problems. So there, till now, what are all the formulas I taught you? Q is equal to CV. Capacitance is A epsilon by D. Field between the plates is V by D or sigma by epsilon. This is also a formula there. And yeah, force between the plates is Q square by 2A epsilon. Clear? Let's see a question. So we have two square plates here. Hundred volts. Distance D between them is 1 millimeter. That's a 1 centimeter. These are square plates. Side is 1 meter. So you projected a particle plus Q and mass M in the center with speed U. This is D by 2. So first thing, find capacitance, find charge, find the field between the plates. And the point where the charge hits the plate. Or let me ask you like this. Find U. Find U minimum if the charge just misses colliding with the plate. Charge avoids colliding with the plate. Charge is plus Qm. It's projected horizontal. Let's get them. So one capacitor question, second one is a projectile question. We just mixed up two things. Eight 8.85 and 10 power minus 14. Okay. Yeah, and the numbers will be bad. You will just put it on. Everyone should try. Everyone should try. See? 8.880. So first thing, the capacitance will be A epsilon by D. A is 1 meter square. Epsilon is 8.85 into 10 power minus 12. This is a centimeter to 10 power minus 2. This is 8.85 into 10 power minus 10 farad. Charge of the capacitor is C into V. Voltage is again 100. So 8.85 into 10 power minus 8 coulombs. Field between the plates is nothing but potential difference by distance, which is 100 by 1 centimeter, which is 10 power 4 volt per meter. Check. Easy? Straightforward formula substitution. Have a look at this. Anyone has a doubt on this, please ask. Then the second question. So you took two plates here. This plate is positive because you connected the positive terminal, and this is your negative. So the field between the plates is E, which we calculated 10⁴ volt per meter. So when you take the charge Q here, the force acting on this is EQ is equal to MA. So we get acceleration is equal to EQ by M. So you know how is this question become like? The question has become like someone projected a particle with speed U from a height of d/2 from a building. The gravity in this place, G effective, is EQ by M. We are neglecting gravity here, neglect G. We are only taking the electric field of force. So the electric field is acting like this, and you're saying it just misses the plate. Means it has gone like this, and it just missed the plate like this, na? So what is the range then? Shouldn't this become the range then? Is everyone getting the question? The whole question becomes as if you're throwing a particle from a building horizontally, where the range of the particle is A, the side of the plate. How do you find the range? So for our time of flight, we are using the equation Sy is Uy time plus half Ay time square. Sy is the vertical displacement minus d/2 because it is down. Uy is 0. Half Ay is the G effective. EQ by M T square. From here you'll get the time, which is MD by EQ ka root. Range is nothing but Sx is equal to Ux into time of flight plus half Ax T square. I'm just using basic kinematics, people. So range will be A, Ux will be U, and time of flight will be MD by EQ. Ax is 0 anyway. So from here you get U is equal to root over EQ by MD into A. This is your minimum speed. Please check. The whole question becomes a projectile motion question. Sir, G ka place mein EQ by we have to substitute. Did everyone got the logic here? Labdi, clear with this? Sure, Labdi? Nishita? Sure? Reena? Ammu? Trisha? What happened, Labdi? Not well today? You don't look well. Take care of health. Anamai, clear with this. Dipanshu? Kavish? Adya? Got the concept? Everyone have a look at this. Any doubt, please ask. So once you got the acceleration, it is simply a projectile motion question. We are using the simple equations S is ut plus half at square. Since the velocity is going horizontally, u will be ux and uy will be 0. Gravity is acting down and horizontally there is no acceleration. Clear? Next one. We have a block of mass m here. This is smooth. And here we have two parallel plates. These two parallel plates are connected by a battery. So if you look at the side view, no, the plates are like this. This and this are connected by a battery. These are square plates, side A. And the distance between them is d. The question is, find the voltage of the battery if the system is in equilibrium. Think about it. If you see now, these two plates are not connected by anything. So basically this plate becomes positive and this plate becomes negative. So the attraction is keeping them together. This is the formula we have to use, people. Force between the plates. Q square by 2a epsilon. Try this. So we have one side a block of mass, same other side you have two capacitor plates connected to a battery. Find the voltage of the battery if the system is at rest. To make the question tough, I could have made this surface rough mu. That would have been more fun. But okay, let's get this first. Show you. See now. What is the capacitance of the plates? A square epsilon by d. Area of the plates is a square. What is the charge of the capacitor? CV. So what is the force between the plates? Q square by 2a epsilon. The minus sign actually indicates attraction. So if you draw FBD of the plate, the forces will be tension and the force of attraction. And if you draw the FBD of the block, tension and mg sine theta. That means T is equal to mg sine theta because it is in equilibrium, and T is equal to F because the plate is in equilibrium. So indirectly, we get F is equal to mg sine theta. Make sense? We get F is equal to mg sine theta. हो गया ना? So from here we'll get Q is equal to root over 2a epsilon mg sine theta. And we know Q is equal to CV. From there you get the voltage of the battery. Easy? Just need to put the values and you'll get it here. Check it out. Next one. Let's say we have two capacitor plates. Capacitance is C. Now on both the things, the charges are not same. This is Q1 and this is Q2. Find the potential difference between the plates. What if you have unequal charges, Q1, Q2? If I give Q minus Q2, you know the answer. Q is equal to CV. What if I give Q1, Q2? Find the potential difference between the plates. This is a good one. A simpler version of this was asked in JEE. I'll show you that next. But this is a more general case. Excellent. See, the catch I'll tell you. The biggest problem, right? People have this confusion. When you write Q is equal to CV, what is that Q that you're talking about exactly? That is the main question you need to ask. When you say Q is equal to CV, what is that Q? So before going into that, let's see this thing. So if I have charges Q1 and Q2, how does the charge distribute? I hope you remember this thing. This is Q1 and Q2. What is the charge distribution?
Q1
Outside will be
Q2 by 2
Q1
outside.
plus Q2 by 2. And here it will be Q1 minus Q2 by 2. And this will be minus of Q1 minus Q2 by 2. And outside is Q1 plus Q2 by 2. Remember this? This is what we did in Gauss law. Now understand this. When you take the field between the plates, the field between the plates is due to which charges? It is only due to the inside charges, isn't it? The field between the plates. Because if you remember, this is a conductor shielding effect. The field inside will be only due to the inside charges. The field between the plates is only due to the inner charges. Is only due to charges on the inner surface. And that field will be sigma by epsilon. So sigma here is nothing but Q1 minus Q2 by 2 into area into epsilon. Agreed? So who is creating this field? Q1 minus Q2 by 2, right? So in the formula, when you write Q is equal to CV, this Q is actually the charge on inner surface of the positive plate. Q is not the charge on the capacitor. Because see, if you take the charge on the capacitor, tell me one thing, what is the total charge on the capacitor? 0, right? Total charge on the capacitor is 0. Q minus Q is always 0. It is not charge on the positive plate. It is the charge on the inner surface of the positive plate. So in our question, the answer will be Q1 minus Q2 by 2 is equal to C into V. So the potential difference will be Q1 minus Q2 by 2C. So this is a very important thing. Most people know they write Q is equal to CV, Q is equal to CV. They don't understand what Q is that. Q is not the charge on the positive plate. Q is not the total charge. Q is the charge on the inner surface of the positive plate. Do have a look at this. Simple reason, the field between the plates is created by the inner charges only. The outside charges are useless. So you should take only the inside charges. Have a look at this. Let me show you what they asked in GE exactly. I'll show you that question also. Next thing. So what was the question they asked? This was a GE question. They said, okay, there's a capacitor plate. They connected by a battery voltage. So you will get charge CV, charge minus CV. No? Then they said the battery is removed. Then the two plates became like this. So this thing has charge CV, this thing has charge minus CV. And then Q charge is given to the positive plate only. So battery is removed and the plus Q is given to only positive plate. The question was find the new potential difference. This was asked in the exam. So what happens to the charge on the plates now? Q plus CV and minus CV. Na? What is the charge distribution now? Can you tell me? What is the charge outside? Q by 2.
It is Q by
Total by
Q
2.
by
Q by 2. What is the charge inside then? Q by 2 plus CV minus Q by 2 plus CV and Q by 2. So when you want to find the potential difference, what will you write? Q by 2 plus CV is equal to C into the new potential difference. Na? Q is equal to CV. So we get the new potential difference will be V plus Q by 2C. This was the question. Please check the question. This was how they asked the question. They said a capacitor is connected to a battery of voltage V. Then the battery is removed and you give plus Q charge only to the positive plate. Find the new potential difference. So on the positive plate, the charge becomes Q plus CV. Negative plate, it becomes minus CV. You do the charge distribution. So you need to find the charge on the inner surface of the positive plate. So you are actually interested in this charge. That is equal to C into new potential difference. Please check. This was a JE question. Sure. Clear. Next one. Now, if there is a force, there is also an energy stored. So we have seen the parallel plates. Let's say we have two parallel plates very close to each other. Plus Q and minus Q. Now, if the plates are pulled apart slowly, let's say to a distance D, you separated them. Plus Q and minus Q. What is the force between the plates? Q square by 2A epsilon. This should be equal to the F external force, no? The plus Q is given to the positive. No, in this question only, Ammo. Only in this question it is given to the positive. So the work done by external force will be the F external force into displacement, which is nothing but Q square by 2A epsilon into D. This becomes nothing but Q square by 2C. A epsilon by D is C. So the energy stored in a capacitor will be Q square by 2C, or you can write it as half CV square, or you can write it as half QV. Q is equal to CV. Now from there we can modify all these things. This is your next formula. So whenever you connect a capacitor to a battery, the energy stored is Q square by 2C or half CV square or half QV. All are right. You can note down that. Clear? Now there's still something more here. What about the battery? How much work is the battery doing? Now, when you connect a capacitor like this, if you see finally, when you say this plate is plus Q, this plate is minus Q, all this charge has actually gone through the battery. So work done by the battery is nothing but the charge that flows through the battery into potential difference across the battery. Q into delta V. Change in potential energy is charge into potential difference. So work done by the battery will be Q into V. Did you observe something here? The work done by battery is QV, but the energy stored is how much? Half QV. What happened to the remaining energy?
Heat.
It becomes heat.
Dissipated as
So even though there's no resistor, always there'll be some dissipation. That is one. Next thing, if you look at this energy stored, this is written as half CV square. I can write this thing as half A epsilon by D. Voltage is nothing but potential difference into D ka square. You end up with half epsilon E square into A into D. What is A into D? Volume. This gives you energy by volume. This is called energy density. So energy density is simply the amount of energy stored per unit volume. Half epsilon E square. This is a very important formula. Remember in the beginning of the class, we said something. Electric field is nothing but a form of energy. So it is actually stored in the form of a E square. Means in a region, if you have an electric field E, in another region, if you have a field 2E, the 2E place has 4 times more energy. It's like, if I tell you like this thing, right? If a body has more speed, it has more energy, agreed? But how many times more? Half mv square, right? If the speed is double, you have 4 times more energy. Same way, if you increase the field to double, you'll get 4 times the energy. So this is like a proof there actually, that the energy is actually stored in the form of electric field. Put on this. I'll just note down all the formulas at one place for you to remember. So when you have a capacitance here, area A, distance D here, the capacitance is given by A epsilon by D. Tell me one thing, what if you have two unequal area of plates? Let's say this is A1 and this is A2. A1 is greater than A2. Now what will you do?
We'll take A2.
You take only A2. Because when you put a battery here, the charge will be only in front of the plates. Now you take only the smaller area because you take the field only from here to here. Only the facing plates are equal and opposite charge. So be careful with that. Take the smaller area. And when you write the formula Q is equal to CV, remember Q is the charge on the inner surface of the positive plate. Force between the plates is minus Q square by 2A epsilon. The field between the plates is potential difference by D, or sigma by epsilon. Sigma is Q by A. Energy stored is Q square by 2C, half CV square, or half QV. Energy density is half epsilon E square. Check it out. It will be work done by battery minus energy stored. Actually, now this is a better formula. Initial energy plus work done by battery minus final energy. Think of like this. You have 100 rupees. I gave you 50 rupees, but end way you have only 20 rupees. Means how much you lost? You have 100, I gave you 50. You're supposed to have 150. But finally you have only 20. Means you lost 130, right? That way. Initial energy plus work done by battery, you're supposed to have that much, but finally you have something else. The difference must be heat produced. Please check out this page. Clear? Let's see a question. We got a plate here, which is fixed. We got a plate here, which is a movable plate. This is connected to a battery with a switch. Voltage V, distance is D, and between the plates there is a spring. We have a non-conducting spring in natural length. Remember, one of the plate can move freely. Initially, the spring is in natural length, there's no charge, nothing. So when the switch is closed, the distance between the plates becomes 0.8 d in steady state. The distance between plates becomes 0.8 d in steady state. Find voltage of the battery and the heat produced. So initially the spring is in natural length plates where there's no charge, nothing, everything is fine. The moment you close the switch, something happened and the plates came closer to each other and the distance became 0.8 d. So the question is, find the voltage of the battery and how much heat is produced. Get this. Anyone confused with the question, please ask. Show you. So what is the new distance between the plates? 0.8 d, right? So what is the capacitance? A epsilon by 0.8 d. Agreed? What is the charge on the capacitor plates? Q is equal to CV. Now, if you draw FBD of the left-hand side plate, what are the forces acting on the plate? The attraction force, F, which is Q square by 2A epsilon. The spring force, which is K into X, X is how much? 0.2 d, right? How much did the spring compress? 0.2 d, no? Initially, distance between the plates was d. Now it is 0.8 d, meaning what? Spring got compressed by 0.2 d. So from here, we get Q square by 2A epsilon is 0.2 kd. And Q is equal to CV. So C square, V square by 2A epsilon is 0.2 kd. From here, I get the voltage. Make sense? What about the heat produced? Heat produced will be the work done by battery, initial energy, plus work done by battery minus final. In this case, initially the energy is 0. Work done by battery is the charge into voltage. What about the final energy stored?
Plus spring energy will come out.
Q square by 2C प्लस स्प्रिंग का एनर्जी भी आएगा हाफ के 0.2 d होल स्क्वायर. This is the energy in the capacitor. This is the energy in the spring. This is the work done by battery. Please check. So you have to include the spring energy also here. There, this question combines a lot of things here. Do check it out. Have a look at this properly. Ask me if you're confused. Clear? All got this? Any doubts? Anyone not clear? Any step you're confused? Please ask. Next one. Next one is a pretty good one, right? Meaning it's an easy one, but you can expect something of this sort in mains and bits. We have a capacitor connected to a battery. Then what you did, case one, battery is removed. And distance between the plates is doubled. Case two, battery is present. You didn't remove the battery. Distance between the plates is doubled. So what I want you to find, the new capacitance. What is the new capacitance? What is the new charge? What is the new voltage? What is the new field? What is the new force? Or you can give in the ratio also. The new energy, the new energy density. So example, they'll ask you find the ratio of energy density before and after. How many are there? There are 1, 2, 3, 4, 5, 6, 7 questions. Case one, 7 questions. Case two, there are 14 questions. Example, they'll ask anyone. But this will cover all the things that can happen here. Let's try for case one. Try for 2 minutes, then I'll show you case one, then you can try case two again. Others, you need to put your cams on, right? Don't keep switching off your cams. I'll start removing you from the classroom. Do keep your cams on. Those are cameras are off. You won't get pani puri on the when you come on 9th. If you switch off 2 times, you won't get desserts. If you switch off 3 times, you have to bring your own chair and water. No food. How to do this thing? Try case one, case one. Focus, everyone, focus. If you see, there's a lot of bunch of formulas and different things. After going home tomorrow, make sure to open the notes and do all these things again. Don't just, leave it and come to the next class like a movie theater. And start sending your reports. I'm little free now. Your seniors are done. Unka counseling sab ho gaya. Some if you're not sending your reports on daily basis, you used to send and some reason you stopped. Try case 1. Let's see. So whenever you get these kind of questions, right, where do you start from? Start from the capacitance. So what did you do here? Initially, the capacitor ka distance was D. Then you made the plates double. So what is the capacitance ka formula? A epsilon by D. So what will happen to the capacitance? C by 2, na? And here, remember, you said battery is removed. If you remove the battery, can you get a new charge? If you remove the battery, the charge on the plates is the same. It will be stuck. It can't go anywhere. The charge will remain same. What is the potential difference? Potential difference is Q by C. So charge is same. Potential became, a capacitor became half. The voltage will become double. Na? What is the field? Potential difference by distance. Potential difference is double. Distance is also double. So field will remain same. Same as before. Are you getting how I'm doing this? Next, what is the force between the plates? Q square by 2A epsilon. Q didn't change, area didn't change, epsilon didn't change. The force will remain same. Energy is Q square by 2C. Q is same, but C became half. So energy is double. Energy density is half epsilon E square. The field has become, field is same. So energy density is also the same. Please check how I did this. Please check how I did the 7 questions. Ask me if you're confused. Now using this, I want you to do the same thing for case 2 also. First, any doubts on this, please ask. Clear? Now, can you try case 2? Case 2, the battery is present and the distance is doubled. So remember this thing, whenever you remove the battery, charge is constant. Whenever battery is present, voltage is constant. Because a battery will always maintain a constant potential difference. Not right. P by 2, Q by 2 remains same. Yeah, try. Let's see. So case 2, battery is present. Capacitance becomes C by 2. The voltage will remain same. Q is equal to CV. So this will become half of the previous charge. Field is nothing but potential difference by distance. So this becomes half because distance became double. Force is Q square by 2A epsilon. This becomes 1/4. Energy is half CV square. C became half, so this becomes half. Energy density is half epsilon E square. E became half, so this becomes 1/4. Please check. Easy. There, that is about parallel plate capacitors. This whole part is on parallel plate capacitors. Out of all, this is the biggest one. Clear? Next thing, spherical capacitors. Let's finish off a little intro with that and then we'll go ahead. So the derivation is not that important. A spherical capacitor is nothing but two concentric conducting shells. So let's say this is R1, this is R2. You connect a battery between these two like this. This becomes plus Q and this becomes minus Q. So for such a thing, concentric conducting shells so this is the formula there. Now tell me one thing, when you keep saying capacitor, capacitor, exactly where is this capacitor? So in this scenario, when you take R1, R2, the capacitance formula is given by 4 pi epsilon 1 by R1 minus 1 by R2, which is nothing but you need to mug up it. Direct question will come in the exam. R2 minus R1. You know, where is the capacitor here?
Between the shells.
Between the shells. So this space between the shells, now this is plus and this is minus Q. The space between the shells is called capacitor. The shells are not capacitors. Understand what's a capacitor? A capacitor is a place where you store energy. Where you store energy? In the field. Where is the field? Between the plates. The space between the plates is called a capacitor. The space between the shells is the capacitor. If R2 tends to infinity, means you get a single shell. That is, the second shell is at infinity. The capacitance C is given by 4 pi epsilon R. Check it out. For a single shell, this is the capacitance. For a double shell, this is the capacitance. You should know the formulas. All clear with this? Let me show you something here. So that means, example, if you take a single shell of radius R, what is the capacitance? 4 pi epsilon R. So let's say on this shell, the charge Q is there. Now from the capacitance ka formula, what is the energy stored? Q square by 2C. So this is nothing but Q square by 2 into 4 pi epsilon R. This thing is nothing but KQ square by 2R. Anyone remembers what is this?
Self energy.
Self energy. This is the self energy of a hollow shell. So that means when you say na, the self energy of a shell is KQ square by 2R, where is this energy stored? The energy is not on the shell. The energy is not inside the shell. The energy is stored in the space from the shell to infinity in the form of field lines. Are you getting this? So this energy is actually stored from R to infinity in the form of field lines. So this self energy we have seen in electrostatics. Clear? There. So revise till here and come. I know chapters little, there's a lot of different things. It's not like mechanics. You should have seen these things once. So we'll wrap up with this for today. And one more thing, this week, right, we'll be having a class on Friday, Saturday, and Sunday. We'll have 4 classes this week. Because again, next Sunday, we don't have a class. Next Friday, say, we told you, we're shifting the class from Friday to Sunday. So next week, kya ho raha hai na? Next week, we'll not have a class on Friday, but Sunday, again, you'll have a party and all. So we will lose a class there. So this week, we'll have 4 classes. We'll meet on Friday, Saturday, and Sunday also. Mostly we'll wrap up capacitors by next week, Wednesday or something. 5 to 6 classes it should take. So finish off your backlog if you have any. Before this, we did Gauss law, electrostatics. Uske pehle kya kehte? Elasticity, properties of matter. Do finish it off. HCV has only like 30-35 questions for elasticity, surface tension, viscosity. And do your PACE booklet or whatever booklet you're doing. Okay, so this is a wrap up for that day. So Sunday ka class will be at 9 o'clock, right? 9 to 10:30. Okay, so we'll wrap up with this. So any doubts, anything, please stay back and ask. Always feel free to leave. I'll see you on Friday at 8:40.